Hi everyone. Today, the paper I will present is an empirical study for common language features used in Python projects. The author of this paper are Zhang, Mingzhe, and I. We all come from the University of Science and Technology of China. So the first is the background of our paper. Nowadays, Python is extremely popular as it outranked Java and C, and it becomes the top 2 programming languages used at GitHub. Python's dynamic type system enables fast prototyping, which largely improves the efficiency of software development. Also, lots of libraries or modules and powerful dynamic language features such as metaprogramming removes many barriers in coding. Indeed, dynamic features bring much convenience to developers. They also have some costs. The costs are in 2 major parts, performance and safety. For performance, Python uses interpreter to convert source code into bytecode and then execute, which usually consumes more time than the programming languages using compilers. For safety, Python's dynamic type system can easily introduce type errors, since the type of an object can change at the runtime. Both academia and industry propose some solutions to mitigate these problems in recent years. I list 2 examples here. The first is Pythona 2, which is a Python type inference tool. And actually, Python type inference could largely enhance the type safety of Python programs. However, some language features such as metaprogramming hinders the Pythona 2 from inferring types, because these features can dynamically build objects at runtime. For example, in this code, function train NLU is overwritten by another imported function with the same name. So that Pythona 2 is unable to capture such dynamic chain, thus it failed to infer the return value and argument of it. The second example is Numba, which is a just-in-time Python compiler. Numba reuses the LLVM backend to accelerate the execution of Python programs. But Numba only supports a subset of Python, and language features such as return a function are excluded. From these 2 examples, we can see that current solutions often encounter new challenges for some certain language features. So a natural question is, how are the language features distributed in real-world Python projects? Is it acceptable to exclude some of them when doing optimizations? Actually, we may not pay many efforts to handle them if they are truly rarely used. But if they are commonly used, how they are used? Motivated by this question, we designed 3 specific research questions in our study. And the first is, what's the general distribution of language features in real-world Python projects? This question gives a general view of the occurrence frequency of language features. As projects in different domains may require different language features, we designed the second research question, focusing on the differences of language feature distribution among different domains of Python projects. And in the third research question, we conduct an in-depth analysis to figure out why certain language features are used frequently and how they are used. We hope to learn some using patterns from the current projects. To answer these questions, we first collect 22 language features and divide them into 6 categories. The 6 categories are function, type system, loop and evaluation strategy, object-oriented programming, data structure, and metaprogramming. For each language feature, we designed the recognition patterns according to their definition and the Python specifications. Let's take the first category as an example. This table lists the language features related to functions. We bind each language feature to one or more AST node. For example, we can find the keyword argument in the AST node argument, and we can find the decorators in the AST node function def. These language features can be easily recognized by finding the corresponding AST node. However, there are some other language features requiring global information, such as the recursion in this table. To identify recursion, we need to build a core graph and analyze whether a function is able to call itself. Such recognition is only conducted after the whole AST is visited and a call graph is built. Therefore, we have two scanning strategies here. One is for those only requiring local AST information, and one is for those requiring global AST information. To calculate occurrences of language features, we developed a Python language feature scanner named PYSCAN. PYSCAN has 4 parts, and this slide shows the architecture of it. The 4 parts are highlighted using yellow in this picture. The first part is AST generator, which converts the Python source code into the standard AST. And the second is AST visitor, which walks through the AST and collects information required by the recognition patterns. And the most important part is the language feature recognizer, which matches the collected information and predefined recognition patterns to capture the occurrences of language features. Also, we have a standard library scanner here. It is a relatively independent but necessary module because Python program often use many standard APIs, but it consumes much more time if PyScan scans the standard library every time a new source file is inputted. So to mitigate this problem, we designed the standard library based on the insight. We designed the standard library scanner based on the insight that the standard library do not change frequently. So we can use the standard library scanner to scan the standard libraries once and then store the collected information, so that PyScan can directly access this information to avoid frequently scanning. This slide lists information of our dataset. We collect 35 popular Python projects from 8 domains at GitHub. For example, we collect Flask, Django, Request, Pyramid, and Methonite for the web domain. Totally, this dataset contains 4 million lines of code and 25,000 files. So given this dataset, then we use PyScan to collect all the language feature occurrences in Python projects. The following slide is the empirical result of our study. For general distribution, in this slide we can see that single inheritance, decorator, keyword argument, for loop, and nested class are the top 5 used language features in real-world Python projects. They all account for at least 10% of the total usage. Actually, these features are easy to use and often provide many kinds of functionalities. For example, decorator is designed to modify the behavior of a function without changing the implementation of the function body, so it is quite commonly used in the testing process. On the contrary, position owning argument, heterogeneous list, and tuple, keyword owning argument, and assigning function as variables are the top 5 least used features. These features are more complicated than the 5 features listed in last slides, and some of them are even error-prone. For example, heterogeneous list allows users to put different types into a single list, which can easily bring type errors if the users do not consider all the possible types when iterating the list. Therefore, in this research question, we find that developers of popular Python projects tend to use relatively simple language features, which focus on the safety checks, testing, and some other dynamic features, but they avoid using those complex and error-prone features such as the heterogeneous list and tuple. In addition, we also noticed 2 special language features when analyzing the general distribution. The first is gradual typing, which aims to enhance type safety by letting developers to annotate the types of some objects. The second is keyword owning argument, which aims to avoid misuse caused by the rapid API changes. These 2 features are designed to improve the safety of Python programs, but to our surprise, actually they are rarely used in real-world projects with a usage below 1%. We think a possible reason here is that using these features are not easy. For example, it will be very time-consuming for developers to add annotations for projects Apart from the general distribution, we also investigate the specific distribution across different domains. In these slides, we can see that projects in different domains often prefer to use different language features. But among them, there are 3 language features which are used frequently but differently. They are decorator, nested class, and exception handling statement. So then we conduct in-depth manual analysis in them. For decorator, we firstly collect the usage of 3 built-in decorators and all user-defined decorators. As listed in this table, we can see that the developers prefer to define their own decorators instead of using built-in decorators, and the former is about 3 times of the latter. And the use of the property decorator accounts for the most usage of built-in decorators. Then we analyze how the decorators are used. We collect 7 using patterns here, and from it we can see decorators are mostly used in testing. And a very common usage is the UPD3, in which developers often use decorators from the testing library such as PyTest to set inputs for functions. This can largely simplify the process of testing. Also, decorators can be used to label deprecated functions or control compilation strategy, as can be seen in UPD4 and UPD7. For exception handling statement, we first collect the standard errors developers raise in source code. From this figure, we can see that import error, value error, attribute error, key error, and OS error are the top 5 standard errors developers care about, especially the import error, which accounts for more than 30% of total errors. We find 5 using patterns of exception handling statement. To our surprise, developers pay a lot of efforts on handling differences between Python versions, such as the base string here in UPD1. And as we know that Python evolves very fast and different versions of Python actually has very different implementations. So to improve compatibility of projects, developers add many exception handling statements to eliminate such differences. In other cases, developers prefer to use exceptions to handle the possible errors when interacting with outside modules or devices. And also they can add some safety checks such as a type check using the exceptions. Nested class or function are mainly used in testing, as developers can use a class or a function to wrap the part they want to test in the testing process. This prevents the functions being tested from influencing the outside functions. Also, some operations used commonly in a specific function but not used outside are implemented in nested function, such as the function combine here in UPN4. So in conclusion, in our study, we summarized 22 kinds of common language features, which are divided into 6 categories. We built an automatic language feature scanner named PYSCAN to collect the usage information of them. Based on the result of PyScan, we analyzed the language features' general distribution and specific distributions across different domains. For 3 commonly but differently used language features, we conduct in-depth analysis to summarize their using patterns. We hope the findings and implications from these empirical results can help the developers and researchers who are using Python. And this is the end of my presentation. Thanks for listening.